Good morning. Today we will be talking about Chapter 18 from our textbook, the section on global climate change, as well as the article that I sent out from the Economist magazine titled What Goes Up. We'll be spreading the lecture about global climate change over the next 3 class periods. So today I really want to focus on just kind of the first part of our of the What Goes Up article. All right, so we're going to kind of do this piece by piece, and this is generally the organization for the lecture for the next several days, and I'll be breaking up the individual these sections into like individual YouTube lectures. All right, so this first day, Wednesday, April 15th, we'll look at this first part of the first piece, right? The greenhouse effect, general principles and drivers. And this is the material from the first 2 pages of the What Goes Up reading. All right, so if you have read through kind of chapter 18, then I want you to have read through the What Goes Up article. This piece, this part of the lecture will focus on the information or the material from the first 2 pages of our What Goes Up article. Okay, and this is where they primarily talk about drivers of climate change, right? And so we want to give you a bit more context to what they're talking about. All right, so let's start with the greenhouse effect, right? And this was where it was really interesting that back in the 1860s, John Tyndall was finding that some atmospheric gases, including carbon dioxide, would let in energy, but absorb infrared energy, and so that they would impede heat from getting out, kind of the foundation of the greenhouse effect. And so by the 1860, over 150 years ago, we already had an inkling about the greenhouse effect and potential climate change, right? And then even by also early on, where was that? Yeah, by the turn of the 20th century, there was already speculation that the industrial use of coal might warm the planet due to these the heat trapping ability of various gases in the atmosphere, right? And so this idea is not new. This is well-established science that's been known about for over a century, and that you and I can individually observe by just walking into a greenhouse, basically. Like the greenhouse that was here on campus. Where there's essentially, it's a glass building, right? It allows heat energy in, but it doesn't allow that heat kind of back out, or it traps it inside the building, making it warmer, right? It's the same idea. The atmosphere is acting like the glass does in the greenhouse building, okay? Hence the greenhouse effect name, and the name for the buildings, right? So this is, we can experience the greenhouse effect ourselves, and it's been known about for over, a century, right? This is well-established science. All right, so what's not been established is some of these, or what's been established more recently is some of the values here in the figure 18.2. All right, so some of this stuff has been kind of more slowly uncovered. All right, so the sun is radiating about 340 watts of energy per meter squared. That's hitting the Earth. Per meter square of Earth is about 340 watts of energy is incoming from the sun. Okay, and so Earth naturally reflects or emits the same amount. And this, at first, is kind of an astounding realization that, like, wow, how is Earth kind of naturally balancing the amount of incoming radiation and outgoing radiation? How does it do that? Isn't that like a miracle? Well, in reality, this is played out over the Earth's 4.5 billion years. Obviously, there's been some fluctuation in these values over time as we've had periods of the historical climate's been warmer, or we've had ice ages. But by and large, we have this kind of same level of radiation into and out of the Earth, based on the fact that these things have kind of calibrated over time. And if they were unequal, then we'd be in some sort of slow motion runaway effect towards increasing temperatures or decreasing temperatures, right? And so this kind of balance at first glance is kind of pretty amazing or surprising, but in reality it's been a result of Earth's 4.5 billion years of life, and kind of this natural balance here, balancing. So we've got all this radiation coming in. You can see in that upper left, 340 watts of energy coming in. 76 watts or so gets reflected by the clouds and aerosols. A fair bit gets absorbed in the atmosphere, and then a lot of it comes all the way in through the atmosphere and gets absorbed by the surface of the Earth, either water or land. All right, and some of it gets reflected by the surface back up into the sky, right? And so this amount that's reflected, should think of this term called albedo, right? And we've all probably seen snow or ice, where the glare off of the snow or ice is really bright, right? They reflect a lot of that incoming radiation back up into space, whereas dark surfaces or water absorbs a lot of the light. Okay, so this variation in surfaces in reflectivity is called albedo. And so it shouldn't be surprising that a fair bit of or at least some of the incoming solar radiation is reflected back into space. Think of ice caps, but also deserts, right? Large sandy expanses, things like that. Okay, so then we've got the amount of radiation that's kind of, after it's been absorbed by the Earth, gets kind of re-radiated back out into space. All right, and so that's a fair bit here of re-radiation, that big fat kind of red arrow, the amount of energy kind of re-radiated back into space, right? And if you wanted to see that 340 kind of watts of energy being balanced, you'd have to look at the outgoing long wave radiation at 240 plus that reflected solar radiation of 100, that's 340, and that matches that incoming solar radiation value right there. All right, so a fair bit of energy comes in, gets absorbed, and then it gets released. All right, and the greenhouse effect is this last part of the figure here. It's where a fair bit of this energy, this long wave radiation that's getting re-released by the Earth, by the land or oceans, gets trapped by the atmosphere and gets bounced and radiated back down towards Earth. Okay, just like the atmosphere radiates and reflects some into space, the atmosphere is capturing some of that radiation, that long wave radiation from the ground, and bouncing it back down, keeping it kind of here in the lower part of the atmosphere, right? And so this is the greenhouse effect, basically in brief, right here. This heat trapping ability of gases. All right, so that's a little bit about the greenhouse effect. And then generally, what are some of these primary drivers of our climate? Well, obviously the sun, right? The energy output by our closest star, the sun. Okay, then we've got changing levels of gases in our atmosphere, and that also affects the climate. The oceans are important transporters of heat and moisture, and so they're also important climate drivers. And then there are one or two other climate drivers, which we'll discuss a bit more later on. All right, and so let's think a little bit about, well, what would happen without these drivers of climate? What would happen without the sun? That should be fairly obvious. What would happen without the atmosphere? What would happen without the oceans, right? So obviously with no sun, this would be a dark and frozen planet, right? If we didn't have an atmosphere to trap and have that, if we didn't have a natural greenhouse effect, we'd be experiencing much more extreme temperature swings. It'd be much warmer during the day and then much colder at night. and you'd see its temperature swings more similar to some of the other planets in our solar system, right? And we'd be colder on average than we are now if there were no atmospheric trapping of heat, right? And then the point here is about the ocean transport. And you may have heard of like ocean currents, right? These ocean currents are part of this great ocean conveyor belt that redistributes heat around the world, all right? And you can think of this, as our currents. And you can see here's a graphic of these ocean currents. The cooler temperatures representing colder water that sinks to the bottom of the ocean, and the brighter colors, the warmer colors, are those where the water is warmer and is closer to the surface, picking up the radiation, the energy from the sun. Okay, and so it's kind of you can see kind of the fact that there are two levels here. These ocean currents that are warmer are on top of these ocean currents that are on the bottom, and so you can see here this in the Atlantic, we've got this warm water, surface water, that brings all this warm kind of tropical water towards Florida and the Gulf of Mexico, comes along the East Coast, and then goes back up towards Northern Europe. And this is a primary reason why, like, the UK and Ireland, that are basically the same latitude as much of Canada, are much warmer and greener than some parts of Canada, right? But then as the water goes north, it gets colder and it starts to sink, and it brings a lot of that heat and other nutrients down to the bottom of the ocean, and then that current kind of cycles back. And you can think of some of this as, basically this was the currents that our favorite turtle was riding in Finding Nemo. Okay, all right. So we also, what are some of the drivers of greenhouse gases that contribute to this greenhouse effect? This was a figure from the What Goes Up article, and these values along that y-axis here are billions of tons of CO2. And you can see this rapid increase from 1850 to today in terms of the amount of CO2 being released, CO2 emissions in gigatons here. This smaller graphic here, these words are oil, coal, and gas, and you can see kind of the rapid increase in gas emissions from natural gas in the last few decades, right? And you may be interested to learn a little bit more about, what are the cause of some of these emissions? What are the different sectors of our industry that contribute to them, to these emissions? And this is from the IPCC. We'll talk about that acronym a little bit later. And you can see that roughly a quarter of our greenhouse gas emissions come from electricity and heat production. Roughly another quarter come from agriculture, forestry, and other land uses. Almost 15% comes from transportation. So this is, automobiles as well as air travel and things like that. Okay. All right. So I'm going to end here before I jump into talking about the carbon cycle and continuing on in this lecture. So I will see you in the next lecture. Thanks for listening.